Hi everyone, welcome to my YouTube channel. In this video series, we are planning to talk about the application of statistical methods in manufacturing industry. Please subscribe to this channel to get notified when a new video is released. Today, I will be talking about process capability indices including CP, CPK, PP, and PPK and how we can calculate these values in Minitab for normal and non-normal data. Before talking about these indices, let's understand requirement and specifications. Suppose you have a machine shop. A customer approaches you and asks for a customized Torx rounded head screw with a thread forming for a plastic-made product. Customer knows what are the requirements and specification for this screw and will share the engineering drawings with you. For this specific self-tapping screw, customer requires 3 dimensions to be measured after manufacturing. Customer define a specification for each dimension that we should not exceed. Otherwise, it will be rejected by customer IQC site. You, as a supplier, need to completely understand the customer's needs, especially the drawings, and meet those specifications. Suppose the black horizontal line is a dimension. For dimension A, the USL upper specification limit is 1.62 and LSL lower specification limit is 1.56 mm. For dimension B, upper specification limit is 4.02 and lower specification limit is 3.98 mm. And for the dimension C, the upper specification limit is 3 mm and lower specification limit is 2.90. Now, suppose you have manufactured 200 parts and you have measured those 3 dimensions for all of the samples, recorded in an Excel sheet. Let's focus on dimension B and plot the histogram. The nominal value is 4 mm and the upper specification limit is 4.02 mm and lower specification limit is 3.98 mm. As long as the dimension B is in the limit, it will be accepted by the customer. If it goes beyond the upper specification limit or below the lower specification limit, it will be rejected. For this case, the failure rate is 4.2%. Our process is represented by this histogram, which shows measured data are normally distributed for dimension B. If we count the number of parts beyond 4.02 mm and below 3.98 mm and divide it by the number of samples in this case, we will get a 4.2% failure rate. Whatever goes beyond upper specification limit or below lower specification limit is rejected and counted as rejected parts. So, what is the ideal situation? The answer is be right within specification limits. Let's look at the dataset 2 in the Excel file. These data are right in specification limits, and all the parts are passed, so we say process is capable. For the mass production of these products, we need to make sure the process is both stable and capable. These two concepts are both extremely important aspects of any manufacturing process. So what is the stable process? Process stability refers to the consistency of the process with respect to important process characteristics, such as the mean value of the key dimension or the variation in that key dimension. If the process behaves consistently over time, then we say that the process is stable or in control. The process distribution remains consistent over time. In contrast, in unstable process, the process distribution average is shifting over time. There is no direct relationship between the process stability and process capability, but there is an important connection. Process capability assessment should only be performed after first assessment of process stability. Now let's go back to process capability. Process capability is the ability of process to meet the design specification for the service or product you are providing as supplier. It tells us how good the individual part is. It depends on 2 values. First is the nominal value, which is a target for design specification, and the second one is the tolerance or specification limit, which allowance above or below the nominal value. For dimension B, the nominal value is 4 mm and the tolerance is plus minus 0.02 mm. I can't go below 3.98 and I can't go above 4.02 millimeter. Otherwise, it will be rejected. There are two groups of indices: process capability indices, CP and CPK, and process performance indices, PP and PPK. We require the process to follow a normal distribution so we can take advantage of the properties there. Before using these indices to see how capable and acceptable your process is, we need to test process for normality. If it's not normal, see if you can apply a transform to get it there. If not, you may have to use non-normal distributions and methods. At the end of this video, I will show you how to test for normality and how to deal with non-normal data in Minitab. The main difference between these two indices is whether we use a complete set of data for calculation of PP and PPK, where we calculate real performance of the system, or we use sample or batch of data, where we calculate capability of the process. CP and CPK are used for process capability. Generally, you use this when a process is under statistical control. This often happens with a mature process that has been around for a while. Process capability uses the process sigma value determined from either the moving range or sigma control charts. PP and PPK are used for process performance, usually done as an initial phase until bringing a process under control. In theory, CPK will always be greater than or equal to PPK. PPK tells us how a process has performed in the past, and you cannot use it to predict the future because the process is not in the state of the control. If a process is in statistical control, the values for CPK and PPK will converge to almost the same value because sigma and the sample standard deviation will be identical. So remember, use CP and CPK when a process is stable, and PP/PPK when a process is new. Let's start by process capability ratio. The process capability ratio, by definition, is the design specification width divided by process width. A specification width is defined by customer, but the process width is our capability as supplier. Our capability defines the sigma value for this distribution. We manufacture 1,000 parts and measure them to find our sigma value and our distribution. So why Six Sigma? Because in case of normal distribution, 99.73% of data points will be within plus minus 3 standard deviation of the mean. 3 sigma above the mean and the 3 sigma below the mean. Please note that the biggest difference between CP and PP is how the standard deviation is determined. In PP calculation, we use an estimated standard deviation of samples, but for CP, we assume we have a stable process and we have enough data to calculate a true standard deviation. Process capability of 1 means USL minus LSL is equal to 6 sigma, which means entire process with assumption of mean centered is within the LSL and USL. So we say this process is capable. The process capability less than 1 means USL minus LSL is less than 6 sigma, which means we have a larger variation for dimensions and we will have some failure rate. And the CP more than 1 means USL minus LSL is more than 6 sigma, which implies that the standard deviation of our process is small. We have a small variation for dimension B and are completely within specification limits defined by customer. Please note that the assumption here is the mean is well centered and is not shifted. With this assumption, which one is more capable process? Of course, higher value for CP. We will have less variation and less failure rate. Now assume the process mean is shifted to the right or to the left for whatever reason. As we can see, as a result, we will have more data points beyond USL when the mean is shifted to the right and more points below the LSL when the mean is shifted to the left. For this graph, with 0.02 mm mean shift to the right or left, the failure rate goes up to 50%, but still CP is equal or greater than 1. So CP is not an appropriate index to catch the mean shift in the process. It's an index which only tells us about the width ratio, nothing else. It only takes into account two widths. So how we can address this issue? How we can define a better index to take into account the mean shift? With some modification in the equation of process capability ratio, we bring the mean value to the equation and define a new index called process capability index, or CPK. CPK is the minimum of two values. First value is upper specification limit minus mu divided by 3 sigma, and the second number is mu minus LSL divided by 3 sigma. Why we get the minimum value, not the maximum value? The answer is we want to give importance to this specification, which is more critical. Assume you are driving a car and entering through garage entrance door. In this image, which side of the car is close to the boundary and it's more likely to hit? Of course, it's the right side of your car. There's shorter distance and it's more critical for you not to hit. For a perfectly centered process, the upper specification limit minus mu will be equal to mu minus lower specification limit, and then CP that would be equal to CPK. Other than that, the CP is always more than the CPK. Let's go back to the previous histograms. In each of these situations, the CP is equal to CPK because it's perfectly centered process. For the first case, both CP and CPK are less than 1. The second one, both equal to 1. For the last one, CP and CPK are more than 1. Now the question is, what about mean shifted process? As we mentioned earlier, for the perfectly centered process, within the USL and LSL, the CPK is equal to 1. Assume the mean of the process is shifted toward the USL over time, and the histogram of the new sample data look like the orange one. The CPK is gradually decreased and eventually reached to 0. In this case, the process mean is overlapped with USL. Similarly, if the process mean to be shifted toward LSL, the CPK will be decreased and will equal to 0 whenever the mean of the process overlaps with LSL. Now, see the following histograms for 5 different sets of screws over time. Initially, all data points were well within the specification limit, and the CPK value was more than 1. The CPK value could be more than 1 even the mean is shifted a bit to the right or to the left, as long as all data points are within specification limits. The histogram of second data set of data shows the mean is shifted toward right, and some data points are beyond USL. In this case, the CPK is between 0 and 1. At another time, the third set of collected data revealed that the mean of the data is completely beyond USL, and the CPK value was less than 0, with 90% failure rate. After some modification on the process, the fourth set of data collected and was showing the process was shifted toward to the left side of the nominal value, and CPK value was between 0 and 1. After a while, fifth set of data was collected and showed the data point were below LSL, and the CPK value was again less than 0, and the failure rate was above 90%. Now, how we could increase the CPK value? By looking at the equation, we realize that there are some variables that we could play with them: USL, LSL, mu, and sigma. If we go with lower sigma, the CPK value will be increased. It means we need better process, tighter sigma with less variation. The second option is to increase USL or reduce LSL to have higher value for CPK, but this implies having loose specification limits. The third option is to keep the mean value as close as possible to the nominal mean. In general, CPKs more than 1.33 is considered as good, which is a 4 sigma specification. For 6 sigma specification, in the mean-centered process, the CP and CPK values equal to 2. Now assume over time the process mean is shifted 1.5 sigma to the left or to the right. So the distance between the specification limits and the new mean becomes 4.5 sigma. The CPK value for this process is 4.5 divided by 3 sigma, which is 1.5. What about CP? No changes. The process is still within the specification, so the CP equals to 2. As we mentioned earlier, it just takes into account the specification width and process width, not the mean value. One way to calculate process capability is through number of defects per opportunity. This is usually used for discrete data, and in manufacturing is usually acceptable number is 3.4 defects per million opportunities, DPMO. This table shows for CP equal to 1.8 and CPK 1.3, the DPMO is 48. It means 48 defects per million opportunities. And for CP equal 1 and CPK 0.5, the DPMO will be 66,811. To perform normal capability analysis on data, first select all data in Excel and copy-paste them in Minitab. Then, from a Stat menu, select Quality Tools, Capability Analysis, and select Normal. Enter the column of numeric data that you want to analyze, and enter 1 for subgroup size. For this analysis, specify 3.98 for LSL and 4.02 for USL. Go to Options and put 4 for Target, and hit OK. Minitab will produce capability analysis and show the estimates of each sigma. Here are the specification limits and target value. CPK, CP, PP, and PPK. Before doing capability analysis, we should do a normality test to make sure data are normally distributed. To do so, go to the Stat menu, go to Basic Statistics, and select Normality Test. Select variable B and hit OK. The data will form an approximately straight line along the line. The normal distribution appears to be a good fit to the data. In this case, the p-value is larger than the significance level 0.05. The null hypothesis states that the data follow a normal distribution. Now let's demonstrate the process capability analysis using non-normal data in Minitab. First, copy-paste data from the Excel sheet to the Minitab. It's a single column data. We know that the data should fit a non-normal distribution. We must prove our assumption with data. In this case, we can conduct a normality test to prove non-normality. Go to Stat, Basic Statistics, and select Normality Test. Then select variable A and hit OK. Since the p-value is less than 0.05, we assume with 95% confidence the data fits a non-normal distribution. The process needs to be stable. The red dots in the control chart shows instability in the process. In the Minitab, select the Stat, Control Charts, Variable Charts for individuals, and IMR, and hit OK. These red data points indicate abnormal variations, and their cause should be investigated. Once identified and resolved, you can take additional data or remove the data points from the dataset. In this scenario, we will leave these data in the datasets. Next step, we need to find the best fit to non-normal data. In Minitab, go Stat, Quality Tools, Individual Distribution Identification. Minitab displays a probability plot and p-value for each distribution and transformation. If a distribution is a good fit for the data, the points on the plot follow a straight line within the confidence bounds and the p-value is greater than alpha level. For these data, the y-ball distribution and 3-parameter y-ball distribution are a good fit for a data based on the p-value. And finally, for process capability analysis, go to the Stat menu, Quality Tools, Capability Analysis, and finally select Non-Normal. First, make sure single column is selected. Select the distribution which best fit to your data. Put value 5 for upper specification limit, and there is no lower specification limit for this example, so leave it empty and hit the OK. Here summarize key statistic of prep process and shows parts per million rates. And here provide overall capability statistic and expected ppm. To quickly determine whether the process is capable, compare ppk with your minimum requirement for the indices. Most quality professionals consider 1.33 to be a minimum requirement for a capable process. A value less than 1 is usually considered unacceptable. This completes the process capability analysis using non-normal data. We are going to release video series on different topics including application of statistics in manufacturing and quality control, robotics and mechatronics, industrial machine vision, system dynamics, finite element analysis with abacus, GD&T and tolerance analysis, and many other interesting topics. Don't forget to subscribe to this YouTube channel to get notified when a new video on this topic is released.